All right, we're back in Windows World with Arun Kishan. And man, we haven't seen you since the Windows 7 days.
Yeah.
How you doing?
It's good. It's been a busy couple years here since we met last time.
Absolutely. And last time we were talking about your work, moving the spin lock, the dispatcher, which was amazing engineering.
Thank you.
And you've been up to other things, of course. I wanted to come and talk to you about the new application execution model.
Sure.
In Windows 8.
Yeah.
So talk to me about that. What's going on here?
Sure. So we made a few changes, as people who have worked on Windows 8 or been playing with it at all have seen. We kind of have two worlds. You have your desktop world, which is kind of the world people are used to, and then we have the modern world, the Windows Store app world, if you will. And here you have this kind of immersive experience where it's the one app kind of takes most of the screen. Maybe you have another one docked, but predominantly you got the one app executing, right? We kind of wanted to go to a model here where we achieved a couple goals, because we're now targeting different form factors than we've historically done, right? We're looking at low power slate type devices. And so we wanted to optimize this like consumptive, immersive experience for those type of devices. And the kind of things we did there were, I think there's 5 main goals, you could say, that we wanted to achieve with the new app lifecycle stuff. First, it's always responsive. When you're in one of these apps, you don't have interference from the background or slowdowns or anything like that. It's always responsive. When you switch between apps, it's always fast. It's instant to bring up the new app, right? You don't have to sit through a long launch time. You don't have to think about closing apps. There's this notion that you have to like close apps. You can't leave too many apps running that people are used to from the desktop world. We wanted to have it be that you don't have to worry about that anymore. The system will manage it. As far as you're concerned, all the apps are there in the ether, right? You click on one and it comes back from wherever it was. The other thing we wanted to do is we wanted to simulate that you're always connected. So even if we're not running apps all the time, you don't notice, because you still get your email, you can still take your VoIP call, you can still like run periodic tasks in the background, right?
Now, just to clear some confusion on that point right there, in some sense, and we did an interview. I interviewed the connected standby people, or the DAM people, desktop activity moderator.
Yep.
And I wanted to make clear for people out there, when you're talking about connected standby, only is in the context of ARM devices, or only in the context of Windows RT devices.
That's not entirely true.
Okay.
So there will be some x86 class hardware that also supports this connected standby state.
Okay.
Yeah, and you're specifically talking now about this idea that we suspend desktop apps when we're in connected standby state.
Okay.
But some of the stuff I'm talking about here does not specifically relate to connected standby when we talk about modern apps.
Great.
So I'll get into that a little bit. And so kind of the 5th goal related to all this is we wanted great battery life. So you didn't have to worry about how many apps you had for the most part, right? You would still get a kind of a consistent battery experience from your device. And so those were the major goals that we set out to take on. And so if you think about, there's kind of a spectrum that you can look at when you look at what degree of multitasking flexibility you can have in a system. So if you look at on this side, you have our traditional desktop environment, and I would say this is very permissive, right? You can run lots of apps all the time. They're running in the background. They can pretty much use whatever facilities are available in the OS, right? You get on this side, you get to the mobile operating system environment, and this is a lot more restrictive. Sometimes certain systems, like our competitor systems like iOS and Android and things like that, don't necessarily have as permissive a model. They had a more restrictive model, particularly iOS, until more recent versions didn't let apps run in the background at all. And that's really about trying to achieve those goals I was talking about. But then you lose out on a bunch of scenarios, right? How do you do your multitasking where you have stuff running in the background? So we kind of wanted to be in a balance between these two places because Windows has historically been in this bucket, right? Apps can do what they want. It's very feature rich. A lot of apps you have a full rich multitasking experience. We didn't want to be quite on this end of the spectrum because you kind of lose some of that productivity and experience people are used to. So we try to be somewhere in the middle. So this is where I would say the Windows 8 app model is. So we allow multitasking, but we do it in a much more defined way that allows the system to understand what's going on and automatically manage certain things to meet those 5 goals. So the big thing that we've introduced, which you probably have seen, is by default, we suspend apps that are in the background. So when you move away from an application, shortly after it's in the background, it gets suspended. And when I say suspended, I mean no CPU cycles, right? It's essentially removed from scheduling consideration by the OS scheduler. So this app can't run at all. So immediately you get this thing that the new app has no interference from anything in the background because by default there's only one thing running. The second thing we did was we provide triggers or special events which allow apps to run only in response to those events in the background. So the idea there is you don't have a free-for-all multitasking space where apps might be running and draining the battery in the background. Instead, we have a well-defined trigger, which I'll talk about. But an example of a trigger may be network data arrival. So when that happens for a specific type of socket that you've registered with the system, you can run code in the background. So we go to an event-driven model to allow things to run in the background so they can still deliver on your scenarios like void or email or periodic tasks. And here with periodic, we're not talking about a 15 millisecond timer or the stuff that we traditionally have in Windows. We're talking about much coarser grained time scales which allow us to stay in low power longer but still allow these things to work. So I'll go back to that in a little more detail shortly. And the last thing is automatic process management. So the idea here is, since all apps are suspended by default, they're in the background, they're suspended, you can start to accumulate lots of these apps in the background. And since we don't expect the user to manage what's in memory and what's not, we've taken it upon ourselves. So we essentially will automatically terminate apps in the background based on various heuristics of how recently they've been used or whatnot, based on the amount of memory you have possible, so that you don't have to worry about it. We automatically clean things up. And you might think, wait a minute, that doesn't quite work, because what if I was doing something important in that app and then it's gone because it got memory managed? Well, that's part of the thing that we built into the model from the ground up. Like this suspend concept is built into the app model. So apps have to deal with this from the beginning. It's the contract that they have when they get suspended, that the last piece of code that they may ever run is their suspend handler. So if they have state they need to save, great, they should save it, right? And they shouldn't expect to ever run code again, because the system might automatically trim them out of memory, right? Which essentially means terminate them. So then when they relaunch, right, it's up to them to restore back the state that they had and present a UI as if they were right where the user left them. But our goal with all this is that that's rare. Like your 99th percentile cases, your frequently used apps are cached in memory, right? They're just frozen, but they're in memory. So when you go back to them, your resume is instantaneous. So that's how we kind of try to achieve these goals. And I'll talk a little bit more about each of those in detail, starting with the app lifecycle. So we wanted to draw sort of a state machine here. You could have an app that's in init state. Then we'd say it's active. And then it's halted or suspended. This is a very simplistic state machine. So if you're terminated and you get reactivated, you'd have to go back through the init. This init's kind of a one-time cost where you would initialize, restore your state, whatever. Then you move into the active state. and then when you get suspended, you're moving to halted, and ideally you're just moving between active and halted state, right? And then periodically you'll get terminated, so you'll then get flushed from memory, and then you have to go this slow thing. Our goal is that this is the 99th percentile, and this is rare, right? And so because of this, the users don't have to ever quit apps themselves. So that's kind of the goal at a very high level of the suspension. So you might ask yourselves, okay, this sounds great, so why didn't we do this for the desktop apps too? Well, turns out that there's a few things that make that difficult. First of all is the state-saving issue. That really makes it difficult for us to blow away an app because they don't know about this contract. The other big issue is really around IPC mechanisms. So we have window messages, RPC, COM, LPC, which are ways that two processes can be talking to each other, and base named objects. So these are things like in the object manager namespace that are, synchronization objects potentially of some type, like a mutex or an event or a semaphore. These things an application or process can create and then expect other processes can open that same object so that they can synchronize on stuff. So you can quickly see that in the desktop world, any two processes can use any of these mechanisms to communicate. And so if I suspend one of those guys, I could create a reliability issue because any of the other processes might try to contact the guy who's suspended or access a synchronization object that he's holding when he's suspended.
Yeah.
So this is where you get the donut or the spinning thing, because you're essentially talking in the world of the desktop to a hung application.
Sure.
So that doesn't work very well when you try to retrofit that on an old model, even if it sounds good. In the new model, we actually run each application in its own security context. And what that means is all of these vectors are siloed, meaning you can't arbitrarily send window messages between applications, you can't use arbitrary IPC between applications, and they have their own security identity, which means they effectively get their own data and base named objects directories. So it's virtualized at that level, and they're essentially totally split. So I can independently suspend and resume an app as an entire collection, which is another thing that we didn't have a strong idea of on the desktop, because on the desktop we didn't know which processes comprise a specific app. Now we say that we know that this is this application, so all the processes that we are creating are in that application, right? So we could treat them as a unit for a process management perspective. So those are the new things that the new app model has brought to us that allow us to do this. So let me talk.
So let me ask you a quick question.
Sure.
I mean, in the case where you suspend an app, let's say that you have an app that's running,
Okay.
and this app happens to be in the process of some sort of asynchronous operation, be it going to the internet, downloading a bunch of photos, right?
Okay.
Now, the internet's a physics problem, maybe it's taking a little while, even though it's asynchronous, I'm still seeing things spinning, but so, okay, it's not done yet. I go to another app because maybe, I see this email message came in and I want to read it. What happens? So the app is still actually in the middle of some sort of execution that the user initiated.
Right.
Refresh this page and download these items. Update the cache. I go and run another app, so of course we're in Windows Store world now.
Yep.
How much time does the app have to finish that model?
To save its state.
To save its state and all this stuff?
Yep. So.
That's my question, because sometimes I do see CPU running when I have Task Manager up on one
And you're in
screen.
another app.
Yeah, exactly.
So what we do, that's a good question. So what we do in this is a very simplistic state machine here, right? So this is saying, at a low level, these are the only states that the operating system might care about. But in reality, yes, there's periods of times where you actually are going to have more than one app that are active. So what happens here is when you're active, you actually become not visible for some period, right? Before we actually send you the suspending notification. And the reason for that, why we don't do it immediately, is because you could imagine a user is going to go from app A to app B and back to app A. So we don't want to thrash through the whole save all your state and come back right away. So we have what is considered a debounce interval. So there's some amount of time when the app is no longer visible. This is not visible. And then we go to suspending. So this is some variable amount of time, like on the order of 5 to 10 seconds or something, where we don't send it the suspending notification right away because we want to buffer this.
Mm-hmm.
But we expect apps to start winding down what they're doing when they get a not visible notification from the window manager. And then when they get the suspending, that's when they should prepare to like really save all their state and things like that. So it is true that at this point when they get halted, they may have some outstanding asynchronous activity and whatever, but if they haven't waited for that to finish and made sure they reflected the result of that operation in their saved state, they have to expect that it's lost. Because as we said, the last thing that you're guaranteed to run is your suspending handler. So after that, you could get terminated.
Okay.
So if you didn't wait for this outstanding stuff to finish, then it could be lost.
Okay.
Now, that doesn't always work for a long download and things like that. And that's where these background activities come into the picture. So we'll come back to that.
Cool, and I have some specific questions about building a background cache updater. So
Okay.
not the background downloader, the API that you can talk about a little bit if you want, which is different than what I'm talking about. Sort of is, you have a server. Server says I have updates available. The app's registered to receive those updates. The system will therefore in the background, even if the app isn't running. We'll say, go ahead and update the cache for this app and download however many images you need to download.
Okay,
that's one thing.
That's a good question. And we'll talk specifically about this bullet, which is this is the bullet about how you do multitasking.
Great.
And we'll come back to that.
Great.
But I just want to wrap up a couple things on Suspender Zoom. So, big question here is like, okay, how do we physically at a low level do this? And so you know about, we like to talk about low level stuff.
Low
here.
level's good, man.
So, the way, we have a few new components in our system in Windows 8 here. I'll just outline them briefly. We have this thing called a background infrastructure service, which I'll call BI. We have this thing called PSM, which is Process State Manager.
Okay.
This is the component that is responsible for managing the triggering of apps for background activities. So we'll be coming back to that. The Process State Manager is kind of a low-level system component that's managing this state machine, right? Like on what processes comprise which apps and which state they should be in. These things are a session 0, so they're effectively like services. Another important player here that's not new in Windows 8 is DCOM launch. And I'll talk about that in a second. Now we have the user sessions. So you could have, session 1, session 2. This is a multi-session box, so I'm just giving you the big picture. In practice, there's typically just the one logged on user for a consumer device. Session 3, so on. In here, there's a component called the PLM, which is the Process Lifetime Manager. So it's slightly different than the PSM. The PSM has a global view on the system. The PLM is a entity that understands a specific user and session, all the apps that are comprising that. It's lifetime managing them in terms of when do they move between these states. So that policy piece lives in the PLM. When is something active, when is it halted, when is it terminated, right? The mechanics of how that's done is handled by the PSM. So what happens when you launch an app in Windows 8 is that it essentially, the apps are modeled in our system as WinRT servers or DCOM, like COM servers basically. So when you activate an app, it actually goes through DCOM launch, which says, okay, I'll look up the information about this app and activate it. So then I'll fire up an app here. An app process, right? This app process is tagged as part of this. These guys all kind of live in the same process today, the same service. This process is tagged with what we call the package full name. So this is like the package information, including the version and architecture and things like that, and the application ID. So this is like kind of the friendly name of that specific application. that's placed into essentially the process token. So there's a strong identity of this process, of what it is. That's used as a key to essentially put this process, so decom launch creates this process and then registers the process with PSM and says, hey, here's a new process. PSM internally has a mapping of this user session package ID, let's just call it package ID, to a job object. Okay, so it's keeping track of each of these tuples in a job object.
Okay.
Right? And so that gives, when we place the root process into a job object, what's happening here is now any child process that's created inherits, so it'll also be in this job object. Right? So essentially we have a unit that represents everything that's that application, that job. And so we do the freeze and resume at the job level. So we say, okay, freeze this job. PLM will say, okay, make this thing suspended. So first we'll actually send it a suspending notification to all that. So we'll talk about that in a second. But then when it actually comes time to freeze it, we do this job level freeze. And since that's at the job level, we're atomic with creation of new processes, so you can't have a process that escapes and gets to keep running. And also it's a first class concept in the kernel, so when we make a process not runnable, no threads that are in flight of being created or whatnot can escape either. So they'll end up being frozen as well.
Okay.
So the PLM is responsible for driving these states. The BI is responsible for also talking to PSM to make the package runnable for background activity. Because you could see that we could be halted or terminated, and I need to go do the scenario you're talking about. So BI needs to talk to this low-level component as well and say, hey, I need this thing in this state. So those are kind of the players here.
So just briefly,
Sure.
What exactly is a frozen job?
Okay.
I mean, we don't have to go super deep because I know you do have a time limit. But just real quickly, as people know, we throw the term out, freeze.
Yeah.
What's really happening?
Yeah. So now going back into low-level kernel stuff. So we've always supported in NT the concept of suspending a thread. So the way suspension is actually implemented at the lowest level is we send an asynchronous procedure call, or APC interrupt. We've talked about that last time, so people can maybe brush up on that. But the idea there is we send a message to a thread and say, go do something. So suspend, the way suspend's implemented, we send a message to a thread at the kernel level and say, hey, go wait on this event. And that event is a private kernel event that essentially blocks the thread. It's now suspended. Suspension just means that it's no longer eligible for scheduling by the OS scheduler. It can't find it anywhere.
Cool.
So when you want to resume it, we do the same thing. We set that event and the thing unwinds out of the APC and we're back to good news. Now, freeze builds on thread level suspension by making it a process concept. So we say we freeze the process, we'll end up suspending all the threads in that process. We also mark the process in a way that says any new thread that's created here should also be put in the frozen state right away, meaning it should be suspended right from the beginning. Likewise, in order to handle the races that you might have if a process is creating a new process, when we suspend, if we're just iterating processes and freezing them, that's kind of a pain. Instead, we make it a job construct, which is already tracking new processes that show up, and we freeze the job. So a new process that shows up gets frozen automatically.
Great.
So that's kind of the low-level piece there.
And then all of its state, and you sort of guard the memory that it's using so you don't have anything overriding it, right?
Yeah.
So all the basic stuff. It's advanced, it's cool, it's fast, it's impressive.
Yeah, so this, when we talk about, we might feel that's a little inefficient that, we have to suspend each thread one by one, but on the grand scale of things, this is really fast operation.
Absolutely.
Cool. Okay, so one more thing I want to touch on with regard to suspending apps. So big part of this whole picture is letting an app know that it's being suspended, right? So we have to send it a notification, right? So if you look at the app, here's an app. We have this framework in the app called core application. So this is kind of the engine that represents the app framework. and it has basically delegates that it calls on the app, right? The app provided code. We have a PSM client library that gets loaded into every modern application or Windows Store application. This thing has dependencies on that. So this thing can subscribe to the quiesce or suspending notification through this library. When we decide to suspend an application, what we do is we actually activate a thread in this process to run the suspend notifications in this process. And we actually have a well-defined tiering system. So we have app, framework, library, and system component. So think of a DLL here when I say library. And system is like OS components. The idea here is that these are kind of distinct components that are in a process. And when I want to suspend a process, I need to issue the callback to each of these layers one by one. And we start with the app layer. We say app, quiet yourself down, save your state, whatever. When that's all done, we move to the framework layer. Framework is stuff like Jupyter or WWA host, right, for the JavaScript
So Jupyter being Windows XAML.
Exactly. And then the library layer is like maybe DLLs that the app has provided or that we provided, and the last layer is system. But the key here is we finish each layer before we go to the next, because in theory this is a well-ordered system where one layer doesn't have dependencies on the layer above it, so you can quiesce the first one and move down. So when we do a suspension, this is an app, I've blown up one process here, but you can imagine that this is replicated several times for each process that we have. We actually send this to them all in parallel. And so this thread is going to go through each of these things and do it in parallel in all the processes. And when it finishes the last one, it calls back to PSM and says, hey, I'm done quiescing this process. So then PSM says, okay, cool. The thread returns back here and blocks on an event. In here, our dispatcher thread. When all the processes have finished, that's when PSM calls the kernel and says, okay, freeze this entire application, which is just one operation on the job.
Nice.
Right? When we resume, we essentially signal this event. The dispatcher thread will essentially run in the reverse order back, right, and run the resume handlers for each of these. Now the app layer here, this PSM API I'm talking about isn't exposed to the app developer. Core application has subscribed as the app on behalf of the application, and what they call when they get their notification is the on suspend, on resume that the app developer provides. But in our lower level framework, this is kind of the tiering system we have.
Sweet.
So this all sounds great. This is a very high level view of how this works, but there's a few problems that if you think about it for a few minutes might come to mind. So I want to touch on those real quick. Go ahead and erase some of this stuff. Okay, so the first big problem is wakes. What if there's a scenario where you actually need to wake up an app and it's frozen, right? We said initially, they're all in different security contexts. We don't care about communication arbitrarily between them. But there's some scenarios in our system that are actually built on the assumption that you might need to talk to another process in the system. A good example of this is clipboard. When I copy-paste, I copy content from one application, but then when I paste it, we don't actually marshal all that data onto the system clipboard up front. We lazily do it when you actually paste. We actually talk to the app that owns the clipboard and say, here, give me the data, right?
Okay.
But that means essentially you need to talk to an app that might be suspended, right? That's just a very simplistic example.
That's interesting.
It's one of them.
Okay.
And you could, as we went through this exercise, we started seeing more and more processes or situations that necessitate a need to wake. So we built this mechanism to solve this called wake references on the job objects. The idea is that at the job layer we just have a set of counters. So let's just say 0, 1, 2, 3. And these correspond to some well-defined reasons. So let's say this is user, this is maybe kernel, execution, or I/O completion, or something like that. Various reasons, right? Just think of them as an enum. kernel components can basically call the job APIs and say, hey, I want to set increment a counter associated with this reason. So the reasons are there more for descriptiveness than anything else. But what happens is whenever we have a 0 to 1 or a 1 to 0 transition on any of these counters, we can issue a notification. So this is a job corresponding to an app. We can issue a notification, which actually is subscribed to by PLM. And that kind of pokes PLM and it says, hey, this package process or application has something that occurred that's defined by one of these reasons. And so it can then evaluate, okay, do I need to make it active or what do I need to do? But at least it's hooked into the process in a very generic way. It's decoupled. So we don't assume anyone's listening and nobody else knows about the consumers, but they're just saying, hey, interesting thing is happening. And so, for example, the LPC, RPC mechanism is plugged into this, so they just increment and decrement these counters when they send a message to an app. They say, hey, I'm sending a LPC, I expect a response. So that increments as 0 to 1. And then this thing can activate it accordingly, right? Because it gets a notification. We give the 1 to 0 also because when the reference is dropped by the kernel, it no longer needs to run, right? So the 0 edge transition tells it that. Another thing is window messages. So synchronous window messages between applications aren't possible, but we do have broadcast window messages that are issued for things like rotation, or things like that get sent to everybody on the system.
Okay.
So you could imagine that if you had an app that's been suspended for a day in the background, but you've been rotating your slate, right, back and forth, this thing has been getting notifications that are just queuing up in the kernel saying that, hey, this interesting event has occurred, right? And when it gets resumed, it's now going to replay that entire queue, so it might change its orientation like 100 times.
Yeah.
That's not great for a variety of reasons. That's not a good user experience. That's a waste of kernel resources.
Yep.
So one of the things that we decided to implement is when we freeze, we have a contract with Win32K, or the window manager system, so that we enable window message coalescing, which essentially tells the windowing subsystem that this process is not going to be pumping messages anymore. So you should go into a special mode where we either merge messages as they show up, we keep only the last one, or we do something like have some complicated merge where we take pieces of one and pieces of another and build a new message. And though this is data-driven in Win32K to solve this problem. Another big area is timers. So if you think about timers, this is interesting. This has two uses. A periodic activity that you're doing, or a timeout. So if you imagine that your app, let's take the first case. I have a periodic timer where I want to do something every few minutes. But if I get suspended and this timer keeps firing, because remember, these are kernel timers. So the kernel's going to keep expiring that timer. But if the app is suspended, then the app can't run. So it's just spurious. And especially if you're in a low power state, your machine is waking up to run this timer and it's all for naught, right? So that's not great.
Yeah.
So that, you could say that's bad from a power performance sort of angle. It's not really a correctness problem. But where this becomes a correctness problem is when we talk about timeouts. So imagine I'm waiting on an error case and I say, okay, I'm waiting for this to happen, but if 5 minutes pass, it's an error, right? But let's say after 1 minute of waiting, I get suspended for a day. Come back, timer expires right away because it's been more than 5 minutes, right? But that's not quite right because the event you were waiting for didn't have a chance to run. So it's not really a true error condition. So this is a reliability concern. So what we wanted to do is we needed to virtualize the time that an app saw to not account for the time that it's effectively hibernated. So the amount of time an app is suspended, we rebase all of its timers. The timeout is just another kernel timer, as well as regular timers to account for the time that it's been suspended. So neither of these problems occur. And you don't have this thundering herd type of problem when you resume the app and it has to run all of this code based on all the timers that expired while it was suspended.
Cool. Virtual time.
Yeah.
It's a hard problem.
Yeah. The last thing is resume performance. Now, we talked about this and we said, oh, it's great, let's make this whole thing runnable, right, when you come back. And all it means is just setting some events so that threads get to run, right? Scheduler picks them up, everything's great. Fortunately, it's not as simple as that. And part of the reason for that is memory. So as we remember, or you've probably covered it with the memory manager folks over time, but the NT operating system pages applications out, which it should, right? It should clean up memory for things that haven't been used recently. But you could get into a situation where you go back to an app that hasn't been used for a long time and a lot of it's paged out. So you actually start faulting all over the place, right? When you go back. So your resume experience actually is not that great, and it might have been better just to blow the thing away and start fresh, because what we're faulting on is all the data that's all over the place, and maybe I could just rebuild faster than faulting it in off disk. So we have a new feature in Windows 8 to support all this called swapping. So the idea with swapping, I'll go on this side here, is if you look at an app or a process, you have a working set. So this is a subset of the physical pages that the app is using that are in memory at one time. So they're not virtually or physically contiguous. So could be like VPN, virtual page 0, virtual page 10, so on, right? They're not contiguous virtually or physically, which means that in the normal page file, this is the page file, they could be all over the place. We have features that try to group together contiguous virtual regions and such like that, because they might be accessed together, but at any moment in time, these could be all over the place, right? This could be VP0, VP10, so on. So faulting on these pages in your working set could cause you to seek all over the place. Now granted, that's a little bit better on SSDs that are better with random, but it's still not optimal, right? Because I have to make multiple reads to get this stuff back. So the idea of swap is when we know that we might need to flush this app out of memory, we have a new thing called swapfile.sys. And we reserve a contiguous chunk in that file to house these pages. So instead of draining them out here, we actually will write them out here in contiguous order.
Nice.
So when you go back to the app, we can essentially prefetch this app, because it's one contiguous read off disk to bring the whole working set back, right? So we have this heuristic in the system that looks at what's the working set size versus the disk bandwidth that we have on the system, and that lets us decide, okay, is it worth swapping this thing, or is it worth just getting rid of it when it gets too big? So that's how we optimize the resume performance. So we take advantage of swap most of the time, which means your resume performance is pretty fast.
So there must be some sort of upper thresholds if you're not going to want to take a. If I have an app where I'm just eating a lot of memory,
Yep.
and I've used them on the system, apps that have a ton of resources, lots of images, big files, can be eating a lot of RAM while they're running.
Yeah.
So do you have some sort of threshold where you're like, no, that's too much to put into this?
So what we do is the memory management policy here, which is what decides how we terminate it, fits into this picture, because what we do is we say, okay, this is the disk speed. Let's assume this thing is a monster application, has like a gigabyte of working set.
Yeah.
Then we say that, okay, how long would it take me to do this read if I wrote a gigabyte out? If that's going to take longer than n seconds, where n is some number that we say is the max amount of time you're willing to look at that little screen when you come back to an app where it's not responsive,
You got it.
then we say that, you know what, we're not going to bother with trying to swap this thing out. We'll just let it page normally. But when we get under pressure and we have to terminate guys first, we'll go after those guys first, because we know we can't give them a high fidelity resume experience anyway.
Yeah.
But we also know that the swap experience isn't great either. So that's how we manage that.
Cool.
So that's kind of the overview of all the suspend resume stuff. Now it's time to talk about your original question,
Yes.
which was background.
Yeah.
Okay, so this is all great, but as we talked about, by default, nothing can do anything in the background, and that's not the best thing.
No.
So part of the model here was to come up with an architecture where we knew who wants to do what in the background, and we can manage that life cycle. So if you look at an app, I talked about an app as one job object so far, but logically there's multiple components to an app. there's the foreground components. So these are executables that ship with the application. These are app code. This is the stuff that's going through this life cycle. We have background tasks. We'll come back to this, that we would call these partially brokered background tasks. Partially brokered means that it's background code, but the app provided that code. But conceptually, they're decoupled from the foreground activity. And that's partially because we go through this life cycle, which we'll talk about in a second. Then on the side here, we can have what we call fully brokered. And this is system code that's providing a system background facility. But it's still conceptually part of the app.
Okay.
So an example of this is background transfer that you were alluding to before. So all of this is the app context. All of this stuff is running under the app credentials. So those are kind of the big categories that we have for background work. Now, there's kind of a big fork in the tree. So we have brokered work. And the idea of brokered work is this is like first-class background work that app provides code or system provides code, but it runs in a special operating mode. There's another category called task completion. Task completion is essentially a mode where we let the app keep running to finish what it's doing, right? So they're two different things. Task completions usually represent something that's initiated by an app when it's in active state, and we want to leave it in the active state.
Okay.
Right? So things that fall in this bucket are audio playback, printing, and a few other MISC things, but those are the big things, right? These are activities that you start while you're in the foreground doing something, and you need to keep doing it to finish.
Absolutely.
And so we have external components to the app because we obviously don't want apps just to say, hey, give me a task completion, let me keep running. They have to be doing something that has a crisp contract that the user is aware of, right? If you're playing audio, the user knows, right? If you're printing, the user knows.
Sure.
So we allow it to have a task completion. In the other cases, it's a brokered contract, means that the app is not in any of these states necessarily. A background task can actually run when you're in the active state. When you're in the halted state, you obviously can't run the task necessarily, so we go into a background state, which I didn't cover before, but this is a new state where the app can be when it's running just background tasks. Likewise, if you're terminated, an event might still occur and we need to run a brokered task, well then you move into the background state. Okay. So you can move from background to active or background back to halted when the background task finishes.
Nice.
So that's like at a high level what's going on here. And the BI component is the one that says, okay, I need to run a task in this application. So I'm going to tell PSM, make it so. So PSM will essentially make sure that if the app's active, that it's fine because it's already running. But it will not let it be halted. It'll instead make sure it goes into background state once it finishes. So what this means is for a life cycle of a background task, erase some of this stuff. The background tasks can be in or out of proc. So when they're in proc, that means they're running inside these foreground components, okay. Right? That doesn't mean that the app is resumed. It can still be halted, meaning we've stopped the main part of the application and we just leave part of the application runnable at the scheduler level, meaning threads can execute in that process, and we run the background task in there. That's actually not our preferred mode because these foreground components actually have the most footprint and everything. So in a scenario where you were terminated, we would have to fire up the whole UI process essentially to run the background task. So the more preferred mode is this out of proc mode where we provide a background task host .exe, which is an OS provided container, and we load the user's code in there and run it. And we can actually make this thing I've drawn here is actually a hierarchical job. I think you've already covered the job topic in a different talk, but the idea here is that there's a master job object representing the entire application, and we have the foreground components in one job, and the PLM is actually lifecycle managing this job.
Okay.
This other job on the side is for these out-of-proc components. You can actually leave this job frozen, but make this one runnable to run an out-of-proc background task.
Okay.
And then the other side of that, this thing may be terminated, may not even exist, and this thing can come and go. So that's kind of the high-level model here for how background tasks work for the partially brokered category where the app developer provides the code. Okay, so that's the life cycle. But then the question is, well, I did want to say one other thing that's important.
Okay.
There's a ramification of this that may not be immediately obvious to the developer. But since this component may not be in memory, if this guy has something he needs to communicate to the foreground that's relevant for when the app becomes active again, he has to communicate that through persistent storage. He needs to write something down in the app state that says, oh, I downloaded this thing or whatever.
Okay.
Because he can't give him a callback, right? Because this guy could be suspended, might be terminated, might not even be there. What the foreground guy can do is he can subscribe to progress and completion callbacks for background tasks. Now these are not delivered while he's suspended, obviously, because he can't get them. But if the background task is running or has finished, he can find out. If it's running while he's active, he can get progress notifications that say, hey, I'm this far along. So if you want to show some UI that you're doing a transfer or processing some data, you can use the progress to do that. We don't provide this progress. That's not a system thing. The background task can notify. We provide an API that lets it say, hey, this is my progress. And the system then routes that through to the foreground if it's running or not, if it's suspended, and then it'll just find out when it gets resumed.
So for the case that I was talking about, you have an application where a lot of its UI experience, its foreground experience, is waiting for things to download, be they pictures or not. Imagine an application where you go and browse, 25 million books capable to do, right? Obviously not downloading all that stuff, but you clicked on a category and now the server's going to send down a bunch of images.
Yep.
All of that gets in your own code, you've cached it. If you've done smart things, you're caching the things so you don't have to keep going back. My point is, a modern user experience would be the
Always
apps in
fresh.
suspension. Yeah, it's always fresh, even when suspended or shut down. Without me having to look at those little rings of asynchrony.
Got it. So you're getting more to this model of what are exactly the triggers. We talked a lot about the architecture and stuff, but we haven't talked about, okay, how do I actually run code in the background?
Yes.
Like, what are the events? So we have these things called brokers in the architecture. I erased the diagram, but brokers are essentially system components that expose what we call background events to apps. So some examples of these are WNS, Windows Notification Service. So this is like the Microsoft Cloud service that lets you push notifications to apps. We have a real-time connection broker. So this is for people who do not have a business class scenario that needs a similar contract to Windows Notification Service, but they need more guaranteed uptime than the Microsoft Cloud service can guarantee, right?
Okay.
So this is like if you want to have a private chat or enterprise chat, so Link or somebody might use something like RTC.
Okay.
The other ones we have are time, so periodic timer. And then the last one that we support currently is system events. This is kind of the grab bag of random things, so like internet available, user logon, things like this. These are all background triggers. So what an app can do is an app can allocate events from the brokers and then say, okay, I have this event. Then it calls BI and says, BI, I want to associate this code with this event. And then BI remembers that association and will trigger the app code to run when these occur. And it's actually fairly expressive because we allow apps to build logical expressions of trigger. So these things are triggers plus 0 or more conditions. So there's also conditions that are stuff like network available, things like that. So you can build up an expression that says, I want to run every 15 minutes if the network is available, because otherwise, why do you want to run?
Exactly.
Right? For most cases.
Yeah.
So that becomes a logical expression, and BI basically when the brokers trigger an event, they call BI and say, I'm triggering this event. They don't understand what code is mapped to that event. That's a contract between the app and BI. So BI says, okay, a trigger happened, and I move this association into a latched state. The latched state just means I'm waiting for all the conditions to be true. These are either explicit conditions, which are supplied by the user, or implicit. Implicit conditions are things like when we service an application, we're rewriting its files, right? So we don't want to trigger background tasks while we're doing that. So we essentially have an implicit condition that says, while not servicing.
Okay.
So if you get a trigger while that happens, we save it until the servicing is done. But essentially what happens is when that's done, we activate. And the activation is what will cause the background task to spin up here or here. And prior to doing that, we've talked to PSM to make sure the right state transition occurs.
Great.
So for your example, one way to do that is to use something like the Windows notification service and say, hey, whenever there's an update to the cache, I trigger a background task. Background task runs, does the downloading, saves it in the store. When the app foreground comes up, it can get a completion notification that something as interesting has occurred so that its cache is up to date. And that's how this stuff could run in the background for those scenarios.
And the really awesome thing about sort of composing all of these, the triggers, the notifications, and then the events, is that there is no request out to the server when I resume the app. So
That's
it's
right.
instantaneous update because it happened in the background. To me, that's just a super logical way
Yeah,
to architect an app that has a lot of dependency on the network.
that's right. We absolutely want
So that's
things
really
to be
brilliant that you guys, I mean, it's a wonderful model. We're going to have to get people to do this more often.
Yeah.
Number of apps that I've been using.
Our goal is that people can build almost all the scenarios they want and be always connected, always fresh using this type of thing. So obviously we'll learn over time, but from our experience, this has been pretty effective.
Great.
So, couple other notes I want to make about this stuff.
Sure.
Right away, so this gives you the always connected thing, but right away you'll start to question. Remember in the beginning I was saying, oh great, we're always responsive, we don't run all this stuff in the background. But guess what? We're running stuff in the background now.
Yes.
So what does that mean? Did I just make all that stuff up in the beginning?
No.
Well, hopefully not. So the idea is in this background mode, being a separate operating mode for the application, we have different types of sandbox that we apply to it. There's
Okay.
two categories. The first is performance sandboxing. So the idea here is, sorry,
No worries.
when we're in the performance sandbox state, we're saying that we're going to make sure there's no way that this background activity can interfere with the currently active foreground activity. So what does this mean? This means low CPU rank. So this is a new concept, which you might have heard about a little bit in your discussion on scheduling groups, so I'll come back to that. I/O priority, low. So what low I/O priority means is that we will give not preferential access to the disk or to any device that supports I/O priority to this app for I/Os issued from it. So we'll never let it starve foreground I/O, basically. And memory priority, which just says that the pages used by this stuff are first to get reclaimed by the operating system. So this really limits the amount of damage that you can do as a background task to something else that's running, if something else is running. Since these are priority mechanisms, if there's no contention, you run fine. Which would be most of the case when you're in the connected standby state where everything's off, there's no foreground active, it's just background tasks. So this is more about a case where background tasks can run and not interfere with the experience when you're actively using the device. So CPU rank, this is an interesting concept. So you heard of a new feature we have in Windows 8 called the dynamic fair share scheduling, or
Yes.
scheduling groups. So the idea with CPU rank is that it's a new component to your priority. So you have rank, comma, priority, right? Historically, NT Scheduler only understood this priority, right? So we run the highest priority guy. Rank is a new concept, which we essentially have elements of other schedulers you might be aware of that take into account usage. So when you're trying to build a fair share system, if you go over quota that you might have, this rank will degrade. So it starts at 0, meaning effectively there's no rank. But the more CPU you're using that's over your quota, the rank degrades. And essentially, a 0 pri is always going to be greater than something that has a non-zero rank. So when we run a background task, we actually give it a rank bias. We say it's always rank greater than or equal to 1. And so what that means is in the priority spectrum of 31 to 0, background tasks actually fit in between priority 1 and 0. So they'll never preempt or interfere with actual first-class foreground activity. But since it's just an operating mode, if the user clicks on the app and brings it to the active state, we disengage all the sandboxing. So the app isn't stuck in some low pri mode. Right?
Okay.
It'll run with full speed when the app's actually in the active state. So this is the performance sandboxing angle. So we're still always responsive. The other thing I claimed in the beginning was that we're great on battery.
Yes.
So if I'm running stuff all the time in the background, how am I great on battery?
Yeah, exactly.
So this is great for reducing interference, but if this stuff runs forever, it's still using battery, right? So we have battery sandboxing. So this has a few angles to it. One is that we have two categories of triggers. We have the triggers that could be potentially high frequency. These we would call the preferential triggers. So this will be stuff like the time, RTC, WNS, push. These are high frequency. So we don't want every app on the system to get access to these. Then we have system events, which some of them are high frequency, some aren't, but these are in general lower frequency. So we're okay about letting other apps get these. So we need some way to bucketize apps into these two categories. So what we do is we have a concept in the system called the lock screen UI. So you've probably seen this,
yes,
where it says, "Hey, I need to continue running in the background, and I need to present an icon on the lock screen." The idea is that apps that need to run in the background are going to have the most impact on the user's battery. So the user should choose the ones that make the most sense, that are going to have the most impact, and nominate those. And today, that's limited to 7 applications are given first class access to background facilities. So that's these 3. Now, there's the system event broker, which we allow to everybody, and so that would fall into the non-lock screen category. And so they're able to get access to some of these triggers, like network change or stuff that happens rarely, like SMS arrival is one of these system things.
Sure.
So things that don't happen that frequently, it's okay. So that's one angle of it. The other angle is, even if there's only 7, if these things can run at 100% CPU forever, your battery is toast.
Totally.
So we have a second degree of it, which is resource management. This is actually provided by the operating system. So we do it on 2 angles. We do CPU, we do network. And the idea is we limit how much resource that a background task can get over time. So we actually give it a quantum, if you will, of how much stuff it can use. So for example, we say maybe 2 billion CPU cycles, which is roughly 2 seconds of CPU time on a 1 gigahertz machine. And network is roughly 4 seconds of CPU of network time. This is not forever. This is per unit time. It's per quanta, right?
Okay.
So the quanta in our case that we decided to meet our power goals is 15 minutes. So it doesn't sound like a lot, right? You get basically this much time to do stuff every 15 minutes. When you run out of quota, your background task doesn't get terminated, it just gets descheduled.
So let's make that clear, though. So
Yep.
every 15 minutes, the system wakes up from the lowest level power state, assuming it's in some low level power state. Or not, just a background thing. You get 4 seconds to download something from the internet.
Yep.
And then it goes off again.
That's the base case.
Okay.
So where this doesn't obviously work for a large download,
Sure.
but it does work okay for something like email. So I just want to get that email header and then save it. Right?
Got it.
So yes, so on your power diagram, we're mostly in this low power state, and then an external event occurs, right? So then we'll trigger up, we'll run this code, and then when you're out of quota, we essentially drop down to the low power until 15 minutes. That's when you get replenished and you'll get resumed.
Okay.
So we don't ever terminate the task, but we try to encourage people to fit inside this bucket. And this allows us to talk about our standby time in Windows, not in terms of hours, not in terms of days. We can actually talk about weeks now because we only have 7 of these guys that are running like this, and they're controlled at this rate. that really, these are the things that impact power the most, right? And the net time actually varies. It kind of depends on the interface you're using. You know, on Wi-Fi, you might get away with more time than on 3G, right? The net stack is actually looking at the power impact of the transfer you're doing. 3G actually is going to be much worse for power.
Interesting.
So this is kind of how we achieve those goals. But you could see, like as you've already hinted at, that we have a couple problems here that aren't addressed. So one problem is bursty activity. Let's say that I don't use my quota for several 15-minute periods, right? And I only run once a day. So when I run that once a day, I want to use more quota because I haven't used it. And from a battery impact perspective, that's the same thing, right?
Okay.
So that's not really addressed here. Or if you have a one-time really expensive activity, that's not addressed. Another thing is critical tasks. Something like a VoIP call, when it shows up, just because you're out of quota, if you're in this period, you don't want to not get your VoIP call for 15 minutes.
Yep.
I mean, that's a big deal, right? It's
Absolutely.
a critical task. The other thing is expectations of users. So when I'm using the device and it's actively there and I click to download and I then go to a different app, I'm expecting that download to work at some reasonable rate, not at 4 seconds per 15 minutes throughput when I'm like on a LAN or something like
Absolutely.
that. Or on Wi-Fi, but I'm actively using the device. So we don't provide that facility. Another thing that might be missing is opportunistic tasks, right? So we have like time triggers and things like this for lock screen apps, but for non-lock screen, or even for lock screen apps that want to do some really expensive thing, if they can, like if it's okay for the battery, like maybe I'm plugged into AC, there's no way to do that, right? Because you just have these periodic triggers that have these, I would say, almost draconian kind of resource limits, right?
Sure.
So how do we solve these things? We introduced this concept of pool. So the pool is this back pocket that the system has of quota. So when we look at the model, we say, okay, this is the quota that we can afford, but let's keep a bunch of quota in the back pocket. Let's say minutes of CPU time in the back pocket. The idea is when you hit your limit, we first go look here and say, hey, is there any in the pool? If there is, I take a slice and I can keep running a little bit. So there's CPU pool and net pool, right? And this is some amount that we expect. We've kind of written it off as being in the budget. The other side of this is, so if you don't use your quota, it actually goes into the pools, right? So it's not lost. So
Okay.
when you do need an occasional burst, it's there, right? This also ties into this expectations because when you're in connected standby, we're not actually getting quota out of nowhere. So it's actually coming from apps. But when you're actively using the device in screen on or on AC, the relative battery impact of these things compared to the screen being on, compared to your game going on in the foreground is not that high.
Sure.
So we can actually donate pool to these things on top of whatever the apps are putting in there that they're not using every 15 minutes. So on AC, we have like a high refill rate. On screen on, we have a smaller refill rate, but it's still there. So this lets things that you start in an app, like a download, actually get more net pool, which if you think about it, a download through the background transfer API is actually a bursty activity.
Sure.
And so by having the net pool and having it be larger or refill faster on screen on or AC, it's actually unbounded. You can make those type of scenarios work.
Great.
And the final thing, well, two other things. The critical task is back to your VoIP scenario. So what we do is we basically say certain triggers are critical, meaning even if there's no quota left, there's nothing in the pool, we'll trigger this task. So that doesn't sound quite right because then we're just blowing our battery. Well, yes, but what we do is we actually borrow from the pool.
Okay.
So what we do is we first try to take the time out of the pool. If it's not there, we go negative. So if you think about it, it's like a loan. As long as this is negative, people can only refill it. They can't ever take any from it. So statistically, we hope that we catch up to the original promise because realistically, unless you have a lot of friends, you're not getting VoIP calls every 2 seconds, right?
Absolutely.
And then the last thing is the opportunistic thing, which is I want to do a periodic really long-running task, or if it's okay for the battery, I want to do it. And I don't want to be on the lock screen to do that, right?
Mm-hmm.
So we provide a maintenance trigger. And this is available to all apps. And this will essentially trigger when you're on AC power. It works for everybody. AC power, remember, we're refilling this thing, so it's full. Apps get quota, same thing, but the pool is larger, so they'll be able to refill.
Mm-hmm.
And then when we go to DC, we cancel the tasks. We give them a notification. This is part of our model for background tests, where they get a cancel notification. We say, hey, we're going DC, clean up, wind down, try it again some other time.
Got it.
So this works for like optimization, like I have a database I'm trying to optimize or speculatively do stuff. This works.
Sure, and then for the case that we were talking about earlier with this hypothetical app that has to download a lot of images asynchronously in the background, the maintenance trigger on AC would be nice, obviously, because these are going to be, it's a kind of a long bursty operation.
Yeah.
But also the app developers could say, hey, look, I was on this page when I got suspended. That means, in reality, I'm going to come back up to this page. Theoretically, it's like, unless the system terminates me. Hopefully it won't.
And even if it did, you could save that state. So
Exactly.
you could try to present coming back where you were.
Exactly. And so I would only download 8 images or 12 images, whatever I had on that page for my cache, such that I didn't have to go get it when they went in the foreground. I mean, it's kind of going to be a fair amount of work for the developer. But on the other hand, as a user, I'd love to play with apps where I never have the asynchronous experience of downloading asynchronously, right? Because when you download stuff asynchronously, it's a synchronous experience, actually, because you have to wait.
You have to wait.
So we can do much smarter things. You guys have built in the pipelines and the capabilities that this stuff can be done in the modern world.
Yeah.
So
we hope we provide it. Yeah, and we're going to learn and add more triggers over time, but our architecture allows us to extend by just putting more triggers in the picture.
Good. Well, I'll let you know, because we're going to play around with this.
Yeah. Hopefully, let us know what you think.
Oh, absolutely. So, where are we? We covered pretty much everything?
This is all the stuff that I, wanted to talk about.
Wow.
But let me know if there's some other questions you got or other interesting things.
I think this is incredibly useful. I have to say, I really have a much deeper understanding of the Windows Store app model. So thank you again for another epic conversation. And I think people are going to get a lot out of this. If you want to know how apps work, rock and roll. And I'd like to see people really take advantage of some of these triggers and some of the really smart capabilities that you have in this version 1 product.
Yeah, it's great. We're totally open to feedback and hope that it's useful for everybody out there.
Absolutely. Well, we'll see you soon.
Yeah, thanks a lot.
Cheers.